Right now, at this exact moment, there are approximately 10,000 commercial aircraft in the air above the Earth, each one carrying hundreds of people, each one weighing hundreds of tons, each one defying gravity at 35,000 feet. And here is the thing that nobody in mainstream science wants to say out loud. We do not fully understand how any of them stay up. Not the engineers who built them, not the pilots who fly them, not the physicists who study it. The equation that describes exactly how a wing generates lift, the force that keeps every aircraft in the sky, has never been completely solved. It does not appear in any textbook in its complete and verified form. NASA's own website once stated directly, in writing, that the currently taught explanation of how wings work is not correct. They quietly removed that statement from the public page. But the underlying problem it pointed to remains unsolved today. This is not a conspiracy. This is not speculation. This is one of the most embarrassing open problems in classical physics, hiding in plain sight every time an aircraft takes off from a runway. Let me show you exactly what we do not know and why it matters more than you think.
Every student who has ever taken a physics class has heard the Bernoulli explanation of how wings work. It goes like this. A wing is curved on top and flatter on the bottom. Air traveling over the curved top surface must travel a longer path than air going under the flat bottom. To meet at the trailing edge at the same time, the air on top must travel faster. Faster moving air creates lower pressure. Lower pressure on top, higher pressure below, and the pressure difference pushes the wing upward. Lift. Clean, simple, elegant. Completely wrong. The equal transit time assumption, the idea that air molecules separated at the leading edge must reunite at the trailing edge, has no basis in physics. There is no law of fluid dynamics that requires this. Experiments measuring airflow over real wings have confirmed repeatedly that the air over the top surface arrives at the trailing edge significantly before the air traveling under the bottom. They do not meet. They never did. The entire foundation of the most common explanation taught in schools worldwide for over a century is physically incorrect. So what actually generates lift? Here is where it gets genuinely complicated.
The second major explanation is based on Newton's third law. A wing pushes air downward. The air pushes the wing upward. Equal and opposite reaction. This is actually more physically honest than Bernoulli's equal transit myth. But it is catastrophically incomplete. When engineers actually calculate how much air a wing deflects downward, and therefore how much lift should be generated, the numbers do not match what wings actually produce. Real wings generate approximately twice the lift that pure Newtonian deflection should theoretically produce. That missing lift, the difference between what Newton predicts and what wings actually generate, is accounted for by something called the Kutta-Joukowski theorem, a circulation of air around the wing, a mathematical construct that correctly predicts lift values. But here is what the textbooks never tell you. The Kutta-Joukowski theorem describes what lift does with extraordinary mathematical accuracy. It does not explain how the wing creates that circulation in the first place. Why does air choose to circulate around a wing? What physical mechanism initiates and sustains it? The answer requires solving the Navier-Stokes equations, the fundamental equations of fluid dynamics, in 3 dimensions for a real wing in real airflow conditions. The Navier-Stokes equations have been unsolved in their complete 3-dimensional form since they were first written in 1822. The Clay Mathematics Institute offers a $1 million prize for a complete solution. It has never been claimed. The mathematics that would fully explain why every aircraft stays in the air is worth $1 million, and nobody on Earth has been able to collect it for over 200 years.
You might think this is purely academic, a mathematical puzzle that engineers have simply worked around with empirical data and computer modeling. You would be partially right. Modern aircraft are designed using computational fluid dynamics, enormously powerful computer simulations that model airflow without needing to solve the underlying equations analytically.
They work. Aircraft fly safely. The numbers produce reliable designs. But here is what this limitation actually costs us in the real world. Every aircraft design must go through thousands of hours of wind tunnel testing because engineers cannot fully calculate performance from first principles. The total cost of wind tunnel testing across the global aerospace industry exceeds $4 billion per year. Not because engineers are inefficient, because the fundamental physics of what they are building cannot be completely calculated. Every time an aircraft encounters an unexpected aerodynamic event, an unusual stall behavior, an unexpected flutter pattern, a control response anomaly, the investigation begins not with a solved equation, but with physical testing and empirical observation, because the complete equation for what is happening does not exist in solved form. And there is a harder consequence. The design of truly revolutionary aircraft that might operate at the absolute boundaries of aerodynamics, at the edges of known flight regimes, in conditions that cannot be adequately wind tunnel tested, those aircraft carry an irreducible uncertainty that no amount of computational power can currently eliminate, because the foundation is not yet fully understood.
In 2000, the Clay Mathematics Institute published its list of 7 Millennium Prize problems, the 7 greatest unsolved problems in all of mathematics. Each one carries a prize of $1 million. Only one has ever been solved in the 24 years since. One of the remaining 6 is the Navier-Stokes existence and smoothness problem. The committee's description of why it matters includes a single sentence that should give every passenger pause. Although they were written down in the 19th century, we do not know whether smooth solutions always exist in 3 dimensions. They are describing the equations that govern every cubic meter of air that every aircraft has ever moved through. In 2021, a team of mathematicians published a paper suggesting that smooth solutions to the 3-dimensional Navier-Stokes equations may not always exist, that under certain conditions, the mathematics may produce what are called finite time singularities, points where the equations break down entirely. In real fluid dynamics terms, in airflow terms, a singularity would correspond to something physically catastrophic. The paper did not claim this occurs in normal flight conditions, but it raised the question of what happens at the absolute boundaries of aerodynamics, the places where experimental aircraft push into regimes that computational models have never fully captured. We have been flying for over 120 years. We have crossed oceans, broken sound barriers, reached the edge of space in aircraft that breathe air, and the complete mathematical description of the force that makes all of it possible is still waiting for someone to write it down. The next time you board a flight, look out the window at the wing. That surface is generating a force that humanity cannot yet fully explain. It has done it billions of times. It will do it again today. Follow for more physics hiding at the edge of everything we think we understand.